Welcome. We are here with Professor James Binney from Oxford University. We want to thank you for taking this interview with us.
My pleasure.
Professor, with your work you have inspired the entire generation of researchers. And in your life you have witnessed the so-called discovery of dark matter and the evolution of models and theories describing it. Can you make for our viewers a broad overview of our comprehension of dark matter from where we started to where we are today?
It started, roughly speaking, in 1937 when a Swiss astronomer, Fritz Zwicky, observed that the galaxies in clusters of galaxies were moving rather fast, rather faster than you would expect if the galaxies were held into the cluster by the gravity, by the attraction of one galaxy on another galaxy. And he speculated that maybe there was some other matter in the cluster of galaxies than the galaxies themselves. And it became clear in the middle 1970s that that was indeed the case. That most of the ordinary matter in clusters of galaxies isn't in the galaxies, it lies between the galaxies in an incredibly hot gas that's hotter than the gas in the middle of the sun. But still, it turns out that there isn't enough matter in the clusters of galaxies to gravitationally hold the galaxies in. So if only there were the gravitational attraction of the galaxies and the hot gas between the galaxies are moving so fast that they'd run away from each other on some time scale that's smaller than the age of the universe. And then in the 1970s, there accumulated evidence that galaxies like ours, which rotate, rather like the planets rotate around the sun rotates around the centre of the galaxy and is held in this orbit, presumably by the gravitational attraction of all the other stars in the galaxy. And it turns out that the gravitational force required to hold the sun in its orbit seems coming from the stars and the gas in the galaxy, so from the ordinary matter that we know to exist in the galaxy, is roughly speaking a half of the force that we believe, that mathematics says, and Newton says, is required to hold the galaxy in its orbit. So the hypothesis gathered strength in the 1970s that there was other matter inside our galaxy and around our galaxy which we can't see. This is the famous dark matter, which generates a gravitational force that adds with the gravitational force of the other stars and holds the sun in its orbit. And the real clincher came in the early 1980s with work done by the Dutch radio astronomers who mapped hydrogen gas at large distances from a particular galaxy within exquisite detail and demonstrated that this gas was moving on beautifully circular orbits around this galaxy at speeds that were many times larger than could be explained by the gravitational force of the stars and the gas in the visible part of the galaxy. So the whole galaxy had to be sitting inside an enormous halo, it's called a dark halo, sort of paradoxically, of material that we can't see but generates a gravitational force. And that picture, that view, that understanding that actually most of the material in the universe that generates gravitational field, something like 4/5 of the material in the universe that generates a gravitational field is not of the same type as the matter that makes up the planet and the sun and all the other stars in the galaxy, but some completely different type of material that we have not yet encountered in laboratories. That view really became the norm, the standard view within the scientific community at a meeting in Yale in 1977, so exactly 40 years ago.
Professor, then are you convinced that dark matter is a good explanation for the phenomenologies that astronomers see today?
Is dark matter a good explanation for what we see? Well, I think that at this meeting this week, some of us have become a little bit worried that perhaps it isn't. Although for 40 years we've worked under the hypothesis that it is the right explanation. In the discussion today, it emerged that many people think the same way that I think, that there are very considerable successes. The theory that that 4/5 of matter is of some strange new form, some strange form that we haven't encountered in laboratories, that theory has had very considerable successes. It has explained very elegantly the distribution, the large-scale distribution of galaxies in the universe, and it does a reasonable job in clusters of galaxies, which is where it all started. But as you move to smaller scales, to the dynamics in the centers of galaxies, especially the dynamics in the centers of very low brightness, very, very small, underpowered sort of galaxies, it encounters difficulties. But to a large extent, most of us have thought that these difficulties are just ones of working out the consequences of the theory. It turns out to be harder than people expected. When you have a theory, you have to develop predictions from that theory which you can compare with things that you can measure and observe. And it turns out that it's harder than people at first thought to go from this theory to concrete predictions of what we would expect. And we spent a lot of time in this meeting discussing the details of that predictive process and whether we really expect something to happen which somebody says that we expect to happen, whether it's a problem if it's not seen, and so on. But there are certain regularities emerging which it does seem rather hard for the dark matter theory to explain, and I think there are signs that the community is becoming a little bit worried that the theory that people have worked with since the late 1990s is really quite right. So I think the jury is out, as we say in England. We don't really know. Nobody knows what the final verdict will be, that in 50 years' time, presumably, people will be teaching in school either there is dark matter or that it's all an illusion, because there is a school of thought which says that there isn't any dark matter, and we think that there should be dark matter only because we're using a wrong theory of gravity. So the question of how much gravitational force should I get from a certain numbers of mass of stars and gas is not a completely trivial thing. I mean, you need a theory to work that out with, and the theory we use is the theory of general relativity that Einstein produced just a little over 100 years ago. And we know that this theory has weaknesses. It isn't able to explain properly the dynamics in circumstances when there is very, very, very little matter present. And it could be, unexpectedly, that this weakness is showing itself already in calculating the force that the sun experiences from matter inside. So you wouldn't have thought that there was a problem in working that out, but maybe there is. And so the future will tell how it will all work out.
Professor, you made the conclusion remarks of the Bright and Dark Universe workshop. Can you tell us your opinion about it? And do you believe it's going to help making conclusive steps toward a more complete understanding of the nature of dark matter?
Well, do I think that the discussions this week will advance our understanding? I think that it has been a refreshing experience, though I think that many colleagues will go away thinking about these problems in a slightly refreshed and different way. it was a very broad-ranging conference. So because dark matter is such a very important, I mean, it's a phenomenon, if it really exists, which affects the dynamics of the universe as a whole. It affects the dynamics of, actually, in principle, the solar system. It affects the dynamics of big galaxies, small galaxies, clusters of galaxies. And there are enormous numbers of people working on different aspects of dark matter, and they don't often talk to each other and so on. They're working on in their particular areas. So in the course of these 3 days, we have 3.5 days, we've exchanged views, and I've learnt a huge amount, and I'm sure my colleagues have also learnt a huge amount. And I think sometimes in many scientific meetings that you don't have the sense that you will go away thinking differently. You'll just have a sense of going away of being a little bit better informed about what your colleagues are doing, and you hope that your colleagues are a little bit better informed about what you have been doing. But I think this meeting is one of those at which I at least have a feeling that I'm going to go away thinking about things wishing to rethink about things, to re-examine previously held views, going away with a slightly more open mind on the big questions.
I want to thank you again, Professor, and wish you a pleasant trip back home.
Thank you. It's been a pleasure.